I guess let's get started. I'm a minute over, so now's the time. Hello everybody, thanks for coming. This is quite the audience. I've given this talk once before at our local Atlanta meetup group, so this is about an order of magnitude step up, but you know, go for the gusto, right? My name is Ian Rose. I work at FullStory, and I'm going to tell you about just our particular use case, and tell you about our startup and what we do, and how Cassandra fits in all that. So what is FullStory? Just real briefly, we're an Atlanta-based startup. We're on the west side by Georgia Tech and MailChimp, for those of you who are here from Atlanta. We were a bunch of former Atlanta Googlers who used to work in the Midtown office before they shut down engineering there, and we decided to do our own thing. We launched about 9 months ago, last summer, and it's a service for deeply understanding your users, and I'll tell you kind of more about what that means as time goes on. So we take what we like to call a capture everything approach to understanding user behavior on the web. Basically, kind of in a nutshell, is you get a little JavaScript snippet. I think Google Analytics, if you're familiar with that, and you throw that on your page. And that's all for installation. There's no like individual wiring of events, like I want to trigger on this or I want to record this. You just put one script and you're done. And we capture everything that happens. So the initial DOM of every page, all the changes that happen, all the user events, clicks, mouse movements, et cetera, all the CSS, all the images, everything. So we pride ourselves on being very, very high fidelity and recreating the user experience with like perfect replay. So I'm going to try and demo this. All right, so let me talk a little technically about how this actually works and what we're doing. I think of it in terms of a recording pipeline. So when there are users on your site, and your site is FullStory enabled, you've got the script there, then you have clients, and they're on their computers, and they're using a web browser as they're going to your site. They're running our JavaScript snippet, and what that's doing is it's tracking all the DOM events in their browser, and it's going to stream them like every couple seconds. We send a new bundle, like here are all the events that have happened for the past 5 seconds or whatever the interval is. Excuse me, it's going to stream them to our front ends. We use App Engine, convenient, scalable, etc. So those are receiving all these DOM events from all the users across all of our customers. Those bundles we want to get into Cassandra. Cassandra is our primary, like first tier front end DOM event storage. We use Compute Engine, which for those of you who are not familiar, it's basically Google's version of EC2. I'm sure they would argue there's lots of benefits, but we'll leave it at that. So it's just VMs in the cloud. We run our Cassandra cluster there, so we need to get everything from App Engine and Compute Engine. That's relatively straightforward. There's this little dance you have to do just because App Engine is a platform as a service, and so it has limited ability to do non-HTTP things. So we just have this little bridge. App Engine speaking C2L is a dicey proposition. So everything streams from the clients, goes to this little pipeline, ends up in Cassandra. On the other end, we then need to do something with it once it's in Cassandra. We leave it there, so we're sort of, for a given page, as the user does stuff, we're streaming events, here's some, here's some, here's some, and they're all filling up in Cassandra. When that page is done, where done is defined as either we get an upload event, so that means like the user clicked a link and they're going to a new page, that would be an unload. Or there's an idle timeout. This is kind of a Google Analytics concept they developed a long time ago. Basically, if the user doesn't do anything for 30 minutes, they're probably gone. Maybe they closed their browser or just wandered away, whatever. Close enough, this is called page stuff. Then we say this page is finished, it's time to process it. So we've got all this stream of bundles, and we have some backend servers that we call cookers, because we call our process cooking. They're going to read out all the events from Cassandra, and then we actually delete them. It's only a temporary storage for us. And then once they're done with that processing, they're going to make some essentially like processing artifacts, which are just a couple of JSON files with like all the interesting stuff. kind of an aggregate of all those bundles. And we're going to show those in Google Cloud Storage, which is sort of Google's version of S3. It's like file storage in the cloud. And that's our end storage for all the recordings. So Cassandra is a little bit of an interesting role for us because it's just like a rolling storage. It's not permanent storage for anything. So we've actually gone through a few different things for that portion of the diagram that was Cassandra. We tried Cloud SQL for a while just because we liked the idea of somebody else managing things. We used the FullStory data store, which is a cloud key value store very early on, but that's very expensive, so we really went to the prototype stage. We tried a few different things, and we finally ended up on Cassandra. The requirements that everything else didn't fulfill and that we are now finding fulfilled here is it's got to be reliable. Like I said, this is our kind of front-end storage. Other things can go down, and things will just build up with Cassandra, and we can deal with it later. But if Cassandra's down, we're not recording, and that's our business, so that's pretty important. And if users, when they leave a page or they close their browser, like that's it. There's no recording those events, so we kind of got to get it at the time, otherwise it's gone. And I mentioned early on, we take the capture everything approach, and we apply that both to single sessions. We try to capture everything you do. But we also apply that to like your whole company. We don't have like really low session limits. There's some companies that will do like 500 sessions a month or something like that. We want to do everything. We want every session of every user that you do. Because we feel like that's the way you can, if you're doing bug tracking or if you're doing support or something, sometimes it's the long tail that you really care about. So we try and get every session, which means that we really need this thing to be up, and we need it to be scalable, we need it to be cheap, because we're shoving a lot of data in there. It's also nice because for now, we're most only one-to-one reads and writes. You can imagine if you do 1 million sessions a month, you're not going to watch 1 million sessions a month. That's just too many. You're going to use that search that I showed you before to find the most interesting ones. You're going to watch those a small fraction, and then you might do some summary statistics over the rest. But it means that we don't need to read these over and over and over and over again. So just another nice benefit. I'll talk really quickly about our schema. It's really pretty simple. So we have this event bundles table, which is what we're inserting into. These first 4 values are all just application-defined IDs. Cassandra doesn't really care about what they are. We shove them all together into a single partition key. These 4 IDs all together define a single recording of a page. You can actually kind of see the org is the customer, the user is the person, the session is what session they're in, the page is within the session. So what's nice about making these a partition key is that all of the bundles for a given page are going to land on the same server. So later, when we get to the processing stage and we want to slurp all these out, we're just doing a single scan over that one server. We use a sequence number, just what bundle are we talking about here, and then there's a big blob of DOM events. And these can vary greatly in size. Some pages, you'd be amazed at the horrible things people are doing under the covers, and so we get some really fat DOM bundles sometimes. I will just point out one gotcha that we occasionally run into with this approach is because we're recording on the page level, pages can be really long. When you're recording at this scale, you kind of see the long tail of weird things. In particular, if you're thinking about like a single page app, it's some business app, people can spend hours on one page, which leads to a huge number of bundles for that particular page. And we're thinking about we might need to do some kind of architectural things to break that up. But for now, it means that if we ever process a page twice, which it comes up occasionally, like we get kind of trailing bundles or something, then we've already slurped out all the bundles for that page, and so we get this huge run of tombstones. I've seen worse than this, online, but it's just kind of one we run into. So sort of something actively that we're thinking about, something we can improve. So this is our current network. Like I said, we're still pretty small, but we're growing fast, as they say. We have a 3-node network with 1 terabyte SSDs. We use network attached storage. Everybody will tell you not to use that, and they told us to, but we're only like 4 engineers, so we try and do whatever we can to make things quick and easy. And it seems to work for us. We're probably a little bit over provisioned because of that. If we use local disk, we can get away with fewer IOPS or something, but it works out. And I guess the only other thing I'll point out is that we're throwing a TTL on all bundles, which is just another nice advantage of using Cassandra, is that because this is a rolling event store, nothing should live in our Cassandra forever. You're filling up the page, and then you're slurping it out as soon as the page is done. pages should be done pretty quick, minutes at the most, hours maybe. So if something's sitting around there for weeks, then it means that that got fulfilled. We lost a task or something through an error or whatever. So just to avoid that cost from building up, it's sort of just a nice one-liner of I just throw a 1 month TTL on everything and that junk just goes away. And I did some quick math yesterday. It looks like we're getting about 0.5 terabyte of data each day. This is just in the compressed documents. And again, that's just sort of turnover. So we're not actually growing, we're just turning it over every day. We had a couple growing pains that I'll sort of share, and maybe you can learn from our mistakes. The first one was just managing repairs. I honestly just didn't give this enough attention in the beginning. I was like, it's only if your nodes are down a lot, and whatever, I'm a great ops person, my nodes will be up. And they were mostly up, but still, every once in a while you need to run that for consistency. And so I did it manually for a while, and because I wasn't consistent enough, they would be really long, and it was bad. Luckily, our data is duplicate sensitive because we sequence numbers, so we're not going to have data resurrecting. Upstream will detect the duplicates, but nonetheless. So now we've kind of cobbled together a cron job that does all of our repairs by calling JMX. It just sort of iterates through the nodes. And that's getting us by for a while. I really like to upgrade to incremental repairs. I'll be curious if people have experience running that with their, how that's working for them. We're not on 2.1 yet, so that's our blocker. So it's on backlog. Don't redline the CPU. Again, we try and pride ourselves on being scrappy and not wasting money. And I let these get too close to the redline for a while. I would say the takeaway here is that CPU spikes can happen for a lot of different reasons. You can have a compaction that starts up. Maybe you have some weird grid repair that runs up. When you start a node repair, particularly in the early days when I was not being as consistent with my repairs as I really needed to. GC, maybe you have an unlucky read that has to go run over a whole bunch of SS tables to get your read satisfied. Who knows? There's lots of things. And I was letting our nodes just sit near that 100%, the 80, 90, whatever, too much. And then when you start to repair something and they get behind, it's just sort of this cascading effect. So that was penny wise and pound foolish. My advice is, go ahead and invest, give reserves what they need. Ditto on the disks. I did the same thing, especially once we changed to SSDs. I was like, I don't want to spend a lot of money, because again, we're not growing our data, only as our customers grow, but over time we're just rolling over our data, so I don't need big disks. I actually learned something as I was preparing this talk for the past couple of days. I would notice sometimes that one of our nodes would suddenly have way more disk utilization than the others. It would be like, several hundred gigabytes more than the other two. I was like, what's the deal? I'm using replication factor 3 on 3 nodes. They should all be about the same. They're storing the same data. And I would find that there were snapshots in the data directory, and I wasn't taking any snapshots. I think, in retrospect, what was actually happening was I was reading some talks by some of the data science engineers how when compactions happen, they'll hard link to the SS tables as they're being compacted. And so they end up in a snapshot directory, which is a little bit confusing. So I think I was seeing compactions as they were running, and they were hard linking to SS tables that were going to be removed later. So anyway, I found this quote on SlideShare, how depending on the compaction strategy you're using, in particular if you're using the size tiered, it can take up to like half your disk, like temporarily, as you're doing a compaction. So don't play around with your disk, give it plenty of space. Running out of disk space is super bad. Okay, so that's where we are right now. What are we going to be doing in the future? First off, in the near term, gate tiered compaction. So we were running on 209 for quite a while, which does not have this, and we just, actually this week, upgraded, I'm in the process of upgrading to 2013 so that we can try this. Our data is very, very time locked. We don't go back and update pages after they're done. So it seems like it's a beautiful fit for gate tiered, but I haven't tried it yet. So fingers crossed, but I think that should really help out our usage. And I mentioned before some in the farther future incremental repairs. Also, new Cassandra cluster. I'll caveat, all this is currently in development, so I'm for results to share on this one, but you know, we're optimistic. I'll briefly outline the use case here. I mentioned early on that when we get to that processing stage, the output of the cookers, which is the processing of the event stream, is a set of JSON documents that we upload to Google Cloud Storage. And that works well for us. We like that because cloud storage is reliable and somebody else gets paged if it goes down, and you know, all those nice things about managed services. It also is really nice because the gigabyte month cost, so like the actual carrying cost of storage, is cheaper than the regular disks, what Google calls persistent disks, or on Amazon would be Elastic Block Storage. It's actually cheaper than that. So that's why we don't just like throw these files on disk or in a Cassandra cluster or something like that. We like GCS. The problem is not only do you pay for the storage cost, but you pay for operations for each request. And the number of uploads is kind of killing us financially. Because for every page we record, we're doing 2 uploads. And if you just kind of do the math out, that's actually a lot of uploads. So we want to address that just to kind of get our costs down. So here is the current plan, something that we're calling GCS Mux. The idea is really simple. It's nothing groundbreaking here. It's just we're going to have a little set of backend servers. Whenever you would normally upload a file, you just send them to this little pool of servers, and they're going to just aggregate a bunch of little ones and put them into one file and then upload that. So, you know, if you're aggregating 10 per file, and then we cut our uploads by 10. If you get 100 per file, cut by 100, etc. So back to the envelope math says this will save us a lot of money. We'll see if that pans out. The issue with this, though, is that what happens now when you want to read that file? So I've given like a silly little diagram of what these Mux files would look like. There's a little header that, you know, some checksums and versions and things like that. And then there's just a bunch of blocks. So there's file 1 block has a header, and then its contents, file 2, et cetera, et cetera. And in order to read a given file at file 2, you need to know first, what is the Mux file that it's in? Like, what is its name in GCS? And then where is its offset? GCS supports the range header for HTTP calls. So I can just request that slice out of the files, which is very convenient. But I have to know what that slice is. Where does it start? Where does it end? So we need some new place to store these, so that will be our new Cassandra cluster. So it will basically just be keys are the original file that you want to upload, like file 2. So that name would be your key, and then your value, the columns that you get back would be what is the name of the Mux file that you want to go get at GCS, what is the starting offset, where you can pull it from, what is the length. So obviously we need to kind of spin up a little more infrastructure to do this, but I guess that's the cost of doing business. And like I said, we're currently working on this. You know, hopefully, I don't know, the next couple of weeks, something like that, we'll have some real results and see how that works out. And that's it.